Okay, welcome everyone to McCarthy Observatory's virtual Second Saturday Stars for October. This is the second time we've done a virtual event. We learned a little bit last time, and so hopefully it's a little smoother tonight. This evening we have three small presentations. First, before we get started though, I'm going to give brief instructions on how to use Zoom. You may have noticed that you are muted on entry into the meeting. If you'd like to ask a question, we'll show you in a moment how to accomplish that. But first, we're going to have Roger Moore do night sky viewing highlights. Mark Polanski is going to give us a tutorial on how to image Mars. And then Bill Cloutier is going to give us a presentation on things that go bump in the night. And that's quite interesting. And then, of course, we'll have time for questions and answers. So first off, Zoom basics. So some of you may be using Windows, some of you might be using an iPad. We'll cover both basics. So when you've joined, you have a choice of being in speaker view, where you see just one speaker, or you can be in gallery mode, where you see all of the attendees. We recommend that you use speaker view. So if you see speaker view here, click it in the upper right hand corner. You can maximize your window through the small icon to the upper right hand side of your screen. That puts you into full screen mode. You can mute and unmute yourself on the lower left hand corner. And if you want us to see you, you can start your video or stop your video if you'd like us not to. As some of our attendees already have used the chat feature, that's another way to communicate with us. When you're in speaker view, you can click on the participants button that's in the middle of your screen, bottom middle, and you can pop out the participants window. And also click on the chat button, and that'll pop out the chat window so you can type the message. If you're on an iPad, you have all the same controls, they're just in slightly different places. The switch to gallery view is in the upper left rather than the upper right. The start and stop video is and mute and unmute are at the top, not the bottom. So you just have to reorient yourself and you'll see things differently. To access chat on an iPad, choose the More button in the extreme upper right-hand corner and choose Chat. Now, one of the features that you may find useful is to raise your hand. You can also, from the More menu, you can choose Raise Your Hand. Your hand will go up on the screen, and I can recognize you and find out what you'd like to ask. Okay, so thank you. We'll get started right now, and I'm going to ask Roger to take over. I'm going to stop sharing my screen, and he'll share his.
Very well. Yes, good evening, everyone. Thank you for joining. All right, it's a little bit of this will be a repeat from last month. If you were here last month, I'm sorry you have to listen through some of this again, but most of it is new. So I'm just going to talk about the early October and October and early November night sky. And to do that, I'm going to show you images or screenshots from a program called Stellarium. This is their website, stellarium.org. It's a wonderful program. It's a free download. Although if you like it, they do ask for donations, but it's available for all three of the main operating systems. And once it's installed, you can look up what's in the sky tonight, or what will be in the sky next week, or what was up last year. It's pretty versatile. It's also available for Android and iOS. Those two versions are not free, but they're pretty inexpensive. And then if you just don't want to install another program, there's also a web version you can run inside a browser. You lose some versatility, but it's still pretty nice. So if you go out tonight, look outside about 9 o'clock facing south, this is kind of what you'll see. I usually start off facing south because that's where the more interesting things are, at least from our northern latitude. But you'll see Jupiter, Saturn, Mars, and this band, of course, if your sky is dark enough, is the summer Milky Way. The center of our galaxy is down around here somewhere. So this is pretty amazing. You can see the two gas giants. Jupiter is about, what did they say, 450 million miles away. Saturn is roughly double that. Jupiter, of course, is the biggest planet in the solar system and has more mass than all the rest of the planets put together. And then there's Mars, probably the most studied planet in our solar system, with orbiters, landers, rovers. In fact, there's 3 missions on the way to Mars right now. NASA's Perseverance is a rover. The United Arab Emirates has an orbiter on the way, and the Chinese have a very bold mission of all 3. It's an orbiter, a lander, and a rover on the way to Mars. If you wait about 2 weeks and look out at the same time, you notice things have shifted to the west a little bit. And 2 weeks from tonight, we'll also have the moon joining Mars, Jupiter, and Saturn in the sky. And finally, in a month from now, if you go out at this time of night, Jupiter and Saturn are pretty much gone for the season, as is the summer Milky Way. But we still have Mars high in the center. Getting back to Stellarium for a minute, you can zoom in on any object in Stellarium. And if you have a nice pair of binoculars, it's worth it to go take a look at Jupiter. You might see something like this, where you can actually discern that it's a disk and not just a point of light. Any star is going to look like a point of light, but a planet will get a disk appearance. And depending on your binoculars, you may even see some of the Galilean moons. If you continue zooming in Stellarium, you'll get a nice view of whatever object is you're looking at. This is Jupiter, and in this case, you'll see also the Galilean moons. This arrangement changes from hour to hour and day to day. So whenever you go look at this, you'll find a different arrangement of moons, but the program will keep up to that in real time. And then if you left click on an object, you'll also get a bunch of information about it. Its rise and set times, celestial coordinates, altitude, azimuth, and a bunch of other information. And then if you right click on that, it'll clear that information. So getting back to the night sky, and on October 10th, if you face south but look up, you'll see one of our favorite star groupings, the Summer Triangle. And this is composed of 3 stars, Deneb in Cygnus, Vega in Lyra, and Altair in Aquila. And also, of course, you'll still see Mars. So these 3 stars, Deneb, they're still deciding on how far away Deneb is. They think it's about 1,500 light years. The problem with Deneb is it's one of the most luminous stars in the sky. And because of that, it makes it difficult to determine exactly how far away it is. And then Vega is about 25 light years. Altair is about 17. So this is facing south and looking up. Now let's turn around and face north. These groupings of stars you see near the center, you will see all year, all night, every night. What will change is what's in the further to the west and what's further to the east. But these central stars here will always be visible. There's the Big Dipper, there's Cassiopeia, and they will appear to revolve around this central point here, which of course is Polaris. And we've talked about before how to find Polaris. If you go to the Big Dipper and you take the end of the bowl, those two pointer stars will point you almost right to Polaris. So that's tonight at 9. In 2 weeks, notice it's the same stars, but they've changed position a little bit. And in a month, same thing, the same stars. Now here's the Big Dipper, they just rotated around. And actually, if you sit it out here in one night and watch these stars, you'll see them do the same thing. They'll rotate around the center. If you're a morning person and you like to get up before dawn, and this is what you see looking east at about 5 o'clock in the morning. In this case, you'll have the moon and you'll have Venus. And there's Orion. Orion is rising in the morning. Wait a month and get up a little bit later this time, 5:30. I did it on purpose because now you'll have Venus and Mercury. You really have to have a clear view to the east to see this. I don't know how many of us do. But this is pretty amazing. So if you plan this right, in one day, you can see Mercury, Venus, Mars, Jupiter, and Saturn. It's a very unusual combination we could see at one time. So just some upcoming events in October. Mars will be at opposition on the 13th, and that simply means it's exactly opposite the Earth from the Sun. You might think it's also when Mars and Earth are closest, but because we're in elliptical orbits, Mars was actually a little bit closer on October 6th. But what opposition also means is that the planet is visible all night. It rises with sunset and it sets with sunrise. The Orionid meteor shower peaks in the early morning hours of the 21st. You'll see some stray meteors a few days before and a few days after that, but to get the best, they think, you want to be up in the early morning on the 21st. That means 2 or 3 o'clock in the morning. And so the best thing to do is just find a space, a place with the widest open sky you can, get a comfortable chair, sit down and look up. But these meteors come to us as Earth passes through a debris trail left over by Comet Halley, which last visited us in 1986. There's also some interesting conjunctions. Conjunction is just when a solar system object appears in our sky near another solar system object or appears near a deep sky object. In this case, there's a Mars-Jupiter-Saturn conjunction on October 22nd. And so if we enlarge this, you'll see it's a waxing crescent moon. There's Jupiter and there's Saturn all in the sky together, along with Mars. On October 29th, there'll be a Moon-Mars conjunction. And again, we enlarge that. Now you have a nearly full moon. I think that's the waxing gibbous phase, and then Mars. So just interesting things to go out and look at. And last is a calendar of the moon phases for the month. We started off with a full moon on the 1st. And notice we have another full moon on the 31st, which most of you know is called a blue moon. These blue moons happen every 2 or 3 years, but this one happens to be a blue moon on Halloween. Happy Halloween. And that is it. Do I entertain questions now or wait till later?
Welcome to take questions now, Roger. Any questions for Roger before we move to Mark's presentation? And again, you can chat, you can raise your hand, and we'll unmute you if you want to ask it verbally. Or you can wave on your camera, and we'll see that too.
No questions? Fine. All right, thank you.
Mark, you want to take control?
Sure. Let me share my screen. Okay, hopefully you all are looking at a picture of the planet Mars right now. I'm going to give you a quick rundown on what it takes to get and process an image like this. This was taken this past Friday around 1 o'clock in the morning when Mars was almost directly on the, it was directly due south, I think. So it was up as high as it goes in the sky. This was done with a 10-inch telescope, a 4x Barlow lens to multiply the magnification by a factor of 4, and I'd say a middle-of-the-road camera. Nothing super high end. This is really modest equipment by astronomy standards. And this process can be done with much smaller telescopes and much more inexpensive cameras. Of course, your results are going to vary, but you can still do some pretty good stuff with some pretty modest equipment. The biggest requirement to get an image like this is patience. Even with the most expensive and high-end equipment, your results can and will vary. In general, high-quality results come from taking care of the equipment. If you think of a telescope like a fine musical instrument, like a guitar or a violin, the performer always has to tune the instrument before they play it to get the best results out of it. And the same is true of telescopes. Getting the optics aligned and getting everything focused is just like tuning a guitar. It takes time and it takes patience to get it right. The other big requirement is a cooperative sky. The atmosphere plays a very big role in planetary image quality. Between the telescope and the planet, there's a very thick layer of air. And whenever it moves, which it always is, it's always moving, it causes distortion. If you think of it like looking at a fish in a lake in the water, if you're on a boat, the fish tends to look like it's wavy or not quite as clear as it would be looking at it directly. So imaging planets uses a technique called lucky imaging. Instead of a single snapshot, we record a short video. This particular image of Mars was a video that was about 25 seconds long. Video is actually an illusion made up of many images quickly changing. And the images change fast enough where our eyes can't make out individual images, and what we see instead is what looks like motion. This is why movies in the past were known as motion pictures, the same idea. Video allows us to capture many images very quickly. In the case of this particular image, I was capturing at about 100 frames per second. In the course of those 25 seconds, about 2,500 images were captured. Of those 2,500 images, maybe 200 or 300 of them were actually clear enough to do anything with, or they're free of the atmospheric distortion. That's why it's called lucky imaging, because you only get a handful of good images if you're lucky. So I'm going to pop over to a raw clip of what the telescope actually sees. So this is what the telescope and camera combination sees in real time coming out of the camera. You can see it's very grainy, it's very blurry. You can kind of see it wobbling around a little bit. The features are kind of coming and going. This is the atmospheric distortion. This is what looking through a very thick layer of air does. So there's a couple techniques we can do to get around this. Again, this is about a 25-second clip altogether. So what we have to do is process it. First thing I usually do is pop it into a program called PIPP. It's a planetary image preprocessor. And this helps me frame and crop the image down. And it does a preliminary quality selection. It looks at the quality of each image and determines which are the highest quality or which are the best focused or the most free of distortion. This takes those 2,500 and knocks it down to about 1,000. From there, I'll take the processed image or processed video into a program called Registax. And Registax will then further reduce or refine those images from 1,000 down to about 300. So what this will do now is choose image features that look like they can be used to correlate the images. So it looks for contrast, it looks for anything that looks like a detail that it can focus on. And it will go through those 1,000 frames and align them to make sure that you can kind of see the planet moving around right now. It's kind of stretching and contracting and warping and distorting. This is looking for a correlation between the pixels of each of those images. And when it's finished, it will have sorted the images by quality again, and I'll have knocked it down to about the best 33% of images available. So it'll take another second or two. And there it is. So I'm going to tell it to choose the best 33% of images that it determines. And then I can stack those images. So I was going to take those 300 or so images and average the pixels together to produce a reasonable representation of what the image is supposed to look like. So it looks better, but it's still not great, right? So the next step is called wavelets. And these are algorithms that can basically virtually focus the image. It looks for pixels that are arranged in a certain way or look like there's supposed to be more contrast between them, and it can help remove some of that blur or some of those distortions. So this is probably the most time-consuming part of image processing, is going through these wavelet filters. It's really just adjusting these sliders until you end up with a result that looks good. So you can already kind of see as I move this back and forth what happens to the image. It gets higher contrast and some of the blurriness kind of goes away. So this is just experience kind of playing with these things to see what produces what looks like the best image to you. There's no real right or wrong answer here. So we say it looks good enough. So we'll process that. And that gets us most of the way there. So now we have a pretty good looking image, but it's still black and white. That's because the camera itself is black and white. It doesn't understand color. So I have to go through different filters, a red filter, a green filter, and a blue filter to collect light that represents each of the three colors. Once I'm done with Registacks, I'll pop the images into Photoshop. After I process the red, the green, and the blue light, this particular image is red. This is what green comes out as, and this is what blue comes out as. So there's very subtle differences between them. In Photoshop, I can actually assign the colors themselves. So if I assign red to red, green to green, and blue to blue, when I go through the screen combination function, it then combines the colors into a full color image. From there, I can refine it further. I can go through and do some brightness adjustments, contrast adjustments, a little bit more sharpening. But that's all personal preference. No real right or wrong answer there either. So that's basically what it takes to produce an image like that. Generally, it takes me about 30 to 40 minutes to set up the telescope and get everything focused and aligned properly. Depending on scene conditions, it can sometimes take longer to focus. Generally, I can image from anywhere between 15 minutes and all night, depending on what I'm going after, if there's a specific target or something special, like some special event like an ISS transit that I'm going after. And processing, I've gotten down to about 20 or 30 minutes just because, you know, I've done this enough times now so where it's almost automatic. I just know what to click on and what to go through. So overall, I'd say this took about an hour or so to put together, which isn't too bad. That same night, I also managed to grab some images of Jupiter, which, yeah, that's not the best I've done, but it's not terrible either. Roger mentioned conjunctions in his presentation, and on the 2nd of October, there was a conjunction between the Moon and Mars, and I managed to capture them both in the same frame through one of my telescopes. And this one I can really drill into to get some pretty good detail on the Moon. And if I go all the way up into the corner, where is it? There it is. There's Mars. So that's a pretty quick rundown on planetary imaging. There's not a lot that goes into it. It's really just patience and playing with it. Any questions?
For those that joined more recently, if you'd like to ask a question, you can raise your hand through Zoom or send a question through the chat function.
Yeah, Mark, I have a question for you, please, if you can
Sure.
hear me all right.
Yeah.
Do you use any kind of focusing aids when you're focusing on a planet, or like metered aids, or do you just do it, you eyeball it?
I eyeball it. Planets are kind of tough, especially because like with stars, you can do full width half max, or you get like some raw data, like pixel values. With planets, it's a little tougher because it's so diffuse. It's not like a point source of light, so there's no like maximum value you can really get.
Mm-hmm.
So I'll zoom it in as far as I can and reduce the exposure time as much as I can, and just kind of eyeball it from there.
All right, good, thanks.
Mark, there's a question in the chat.
Yep, looks like, where is the chat?
I can read it to you if you'd like.
Oh, sure.
How do you know the computer is adjusting the image to a true image of Mars? Would the algorithm skew the image at all, and how would you know?
That's a great question. The algorithms don't know because the color is completely up to the user. So the intensities can vary depending on the camera and the equipment. So my camera is far more sensitive to red than it is to green and blue. So I generally end up with images that look significantly more red. So it'll look, something like that. So for me to color balance it, it's more just experience or comparing it to other images. Like I tend to draw a lot of inspiration from Hubble images for a lot of what I process. So we'll look at like a Hubble image of Mars and get an idea of what the color balance looks like from there, and then try to match mine as close as I can. Looks like Joe has his hand raised.
Joe, you can unmute yourself and ask your question.
Can you hear me now?
Yes.
Yeah, my question was almost the same as the last. I was wondering if the colors were arbitrarily assigned, and you made it clear, how you come to that.
Yeah, for some nebula especially, there's a little bit more freedom in the color assignments. Like I can take certain gases and map them to certain colors to highlight or certain differences in composition. For planets though, because the filters, I know the colors of the filters, like I know when I'm using the red filter, I know when I'm using the green filter, and I know when I'm using the blue filter. So I know what channels to assign to what. The real artistic freedom comes in the actual balance of the colors themselves. Again, because the intensities come in slightly differently for the red, the green, and the blue. So that's usually a manual balancing process to try to get it to look as natural as possible.
Well, as a corollary to that, are the Hubble images true color, or is that something that the astronomer who was taking the pictures, was that individual manipulating the colors, or are the colors that we see on these Hubble images, are they the real colors?
To some extent, it depends on the image. For planetary images, generally, yes, they're the true colors. If they're not, they will usually specify. Like sometimes images of Jupiter will have some infrared or some other color channels maps, and they'll usually say what colors are representing what. In the case of, let's see, I gotta add something here. Because there's a whole color palette called the Hubble palette, and it's to highlight the differences between hydrogen, oxygen, and sulfur too. And I just put an image of this together not that long ago, so I'm trying to find it. What is the elephant trunk? Oh, that's Crescent. Anyway, the Hubble palette generally maps sulfur 2 to the red channel, hydrogen alpha to the green channel, and oxygen to the blue channel. In actual real life, sulfur and hydrogen both have red signatures. So most images are predominantly red. But to highlight those differences, they'll map the colors differently to show what that looks like.
I see. Thank you.
Oh, here we go. So this would be the Hubble palette. If this were in true color, this would look almost entirely red with just a very small hint of blue. So using the Hubble palette, you can see a lot more of the difference. Around here, where the oranges are, that's predominantly sulfur mixed with a lot of hydrogen. The turquoises and the blues are a mix of oxygen and hydrogen. So this is what most Hubble images of nebula will end up looking like, just to highlight those differences in composition. Otherwise, it's just sort of a boring red color.
Mm.
To answer the question of my favorite picture, my current favorite is that Mars image, just because I've only really recently started to get really good planetary results. And this and an image from maybe 2 or 3 weeks ago are both about comparable in terms of quality. So they're my favorites now, just because I'm not going to get a chance at this for another 15 years.
Okay, thank you, Mark.
Yeah, thank you, Mark.
You're welcome.
Our next presenter is Bill Cloutier, and he has a presentation titled Things That Go Bump in the Night.
Thank you, John. Well, good evening. I thought that since it's October, that we would have a couple of tales that involve a clear and present danger and maybe some connection with the McCarthy Observatory. So my talk is going to focus on 3 events in October. First of a kind, the first motion pictures of a fireball from which a meteorite was recovered. The first asteroid discovered by the McCarthy Observatory, and the first predicted impact by a near-Earth object, which actually impacted. A little background on the observatory if you're not familiar with what we do, and we do quite a bit of science, and one of the areas that we've really contributed over the past 20 years is in observing near-Earth objects that have been discovered and have a potential at some point in time of impacting the Earth. And once they're discovered, they put a call out to observatories around the world, and they're looking for additional observations. And they need these observations to refine the orbit and refine the potential for some kind of interaction with the Earth. So since March of 2001, when we received our observatory code, and that's a process you go through to become certified with the Minor Planet Center so that they know that you have a certain pedigree to your observations, we have submitted over 2,000 observations of near-Earth objects. We also have an extensive meteorite collection. We actually have 2 collections. One's a hands-on, where you can physically hold a piece of iron from the core of a protoplanet. And we also have a teaching collection, which is over 200 samples of historic and significant falls and finds dating back to 1492. And we also have an all-sky camera. In fact, we just put a second one online to monitor the sky on clear nights and record fireballs and other bright meteors that may pass through the region. So that's some of the science that the observatory does behind the scenes. When you're not visiting, we're not putting on programs. We're still doing some real work behind the scenes. So the first motion pictures, this happened to be a Friday night in October 9th, 1992, and a small meteoroid entered the Earth's atmosphere over the skies of West Virginia. And it was moving pretty quick, over 32,000 miles an hour to the northeast. And in a span of less than a minute, it traveled from the West Virginia area to eastern New York State. It came in pretty shallow. In fact, if it had come in any shallower, it would have bounced off the atmosphere and returned back into space. But it came in around 3 or 4 degrees to the horizontal. The luminous portion of the flight, which is the portion that you see when you see a meteor streak across the sky, only lasted about 40 seconds. But in those 40 seconds, it traveled over 400 miles. And since it was a Friday night, there was a lot of football games going on the East Coast, and people had their camcorders and other cameras out for the football games. So the flight of this very bright meteor, in fact, it was estimated that the meteor was brighter than the full moon, which was in the sky, was captured on at least 16 different video cameras. And that was important because those videos were used to reconstruct its path, not only on Earth, but also where did it come from? What was its orbit? So they took the videos and reconstructed the path of this particular meteoroid back into space and again, back into its orbit. And it had an orbit that extended out to the inner asteroid belt. And it would circle the sun every 1.8 years or so. It was about 40 days or so past its close approach with the sun when it happened to collide with the Earth. And what they've estimated is that this particular meteoroid had an initial diameter when it hit the atmosphere of somewhere between 3 and 6 feet, and a mass anywhere between 2 and 15 metric tons. Again, these are all estimates based upon the density of the rock that they recovered and the flight through the atmosphere, and the fact that it broke up pretty quickly as it got deeper into the thicker portions of the Earth's atmosphere. And that tends to suggest that it's a fairly fragile, stony meteorite that with the air pressure started to disintegrate. Now, looking at the videos, it appears that there were several fragments that reached the ground, but if you've ever been out hiking in the Northeast, you realize that it's almost impossible to find anything with all the woods. But one fragment was recovered, and that fragment made quite the entrance when it hit a young girl's car that was parked out in the driveway. She was sitting in her parents' house that night watching TV when she hears this tremendous crash. And she rushes outside, and there her Chevy Malibu has this gaping hole in the trunk and a big rock sitting next to it. And of course, her first thought is that somebody just vandalized my poor car, and of course she calls the police. Well, eventually it was determined, and the American Museum of History came out and took a look at it, and they realized that the stone came from the sky and not some local vandal. But this is the one remnant of that particular meteoroid that came through the atmosphere that night, and it weighed about 27 pounds, classified as an ordinary chondrite, and it has a fairly high iron content. Now we have a sample. As I mentioned, we have a fairly extensive meteorite collection. This is our little sample of the Peekskill meteorite. It's not a large sample, but you can see quite a bit of detail. And if you look carefully, you can see a gray layer. In the big picture, it's on the left side. On the insert, it's more on the top. That is the crust, called the fusion crust. And that is formed as the meteor goes through the atmosphere. The air molecules can't get out of the way quick enough. And what happens is that they're compressed in front of the meteor which causes a heating, and that heat actually melts the outer layer of the meteoroid. So if you stop by the observatory, you take a look at the Peekskill Meteorite. Now it's named Peekskill because it was recovered in Peekskill, and naming conventions for meteorites, it's usually the closest place that it fell, whether it's a town or some kind of geological feature. On a more personal note, we just talked about the observatory's connection. I was on a plane that night. I had a conference in Florida, a business conference, and I was taking my family. We were on an American Airlines flight, and back then American had a hub in Raleigh, Durham, North Carolina. So that's where the plane was headed. My family was not sitting together. My oldest daughter was at the window, I was in the middle seat, and some woman I didn't know was on the aisle. And we're cruising along that night, and of course the cabin is dark, and all of a sudden the woman next to me grabs my arm and says, "The wing's on fire." Well, looking out the window, you could see this massive fireball going by. It was horizontal, pretty much to the wingtip. It was quite a ways off, but from her vantage point, I could see why she thought there was something very unusual going on. But we watched that meteor go up the East Coast. It seemed like it was forever, but it was actually only tens of seconds. But that was a very memorable night. My daughter still remembers watching the fireball go up the coast, and I do remember when we landed in Raleigh, Durham, stopping by the cockpit and chatting with the pilots on what they saw. So kind of a personal antidote to that meteorite. October is also a month where the observatory discovered its first asteroids. As I mentioned, we do a lot of observations of potential hazards, asteroids that are discovered by a number of observatories around the world, and they're looking for additional observations. And on this particular night, it was the 13th of October, it was a Monday night, Monty Robeson, who was the director of the observatory, myself, were down there, and we were hunting a asteroid that had just been discovered the previous week called 2003 TH2. It's a fairly faint asteroid, and we had to wait until later on in the evening to get it high enough in the sky so that we had a good chance at finding it. But we spent the evening hunting for this particular asteroid, and by the early morning on Tuesday, we had 10 observations that we sent off to the Minor Planet Center. They were all accepted by the Minor Planet Center, which isn't unusual. We had a very good track record as far as submitting observations. Monty Robeson is a stickler for details and an excellent observer. So around 1:30 in the morning or so, after we had finished up, having to go to work the next morning, I left. Monty decided he would stay and close up, and he wanted to go over the data one more time, just make sure that we had everything cataloged properly. When he started looking at the last images we had taken that night, just to go back a little bit, you can see that particular night, that asteroid passed fairly close to the Earth. I mean, millions of miles away, but relatively speaking, fairly close. So that's why we had a good shot at finding it, because it was fairly close that night. It was also classified as a near-Earth object. These type of objects, they can have an orbit that will take them quite a ways from the sun, but at some point they do cross the Earth's orbit, which is why they're potentially hazardous. These Apollo asteroids, and there's about about 12,000 of these asteroids. They do present a threat long term, nothing short term, but as you can see, that particular night, it passed within 1.7 million miles. And the next real close approach isn't until 2027, and it's going to be quite a lot further away. So that was our target that night. But this is the image that Monty was looking at after I left that night, and he noticed that there were 3 very faint specks that were also moving in the image. You can see one at the top called 2003 TG10, one on the left side of the image, 2003 TO13, and one at the bottom, 2003 TH10. So his curiosity was piqued because he didn't think there was anything else in this image besides our target. He called up the databases from the big observatories and started going through their libraries. And sure enough, he didn't come across any of these asteroids as being in the field. So it appeared that they were new discoveries. So he went through the process of reporting them to the Minor Planet Center. And then what you have to do is you have to have multiple observations of these discoveries. Otherwise, a one-time image doesn't count. You have to go through and have multiple images over multiple nights to verify if these things actually exist and they're not just some kind of noise on the camera or a cosmic ray or something else that is fooling you. So once the discovery was made by Mr. Robeson, of course, we scrambled the following nights looking for a good night with good weather to re-image these 3 objects so that we could not only discover them, but confirm them and get credit for the discovery. So you can see that night, if you look up on this right-handed screen there, you can see these 3 objects. They just happen to be in the line of sight of the object we were looking for. So you can imagine it was quite an exciting time. I know Monty called me the next day while I was at work. And he invited everybody from the observatory down there during the confirmation nights so that we would have everybody be able to participate in the verification of the discoveries. And it takes a long time for these discoveries to work through the system. But eventually, if they confirm that, yes, you were the ones that found them, and no one else has any claim to the discoveries, you would have the right to name them. So over time, in 2006, the International Astronomical Union approved the name change of the first one to 115-449 Robeson. And then in 2018, in the fall of 18, Monty submitted names for the other 2 asteroids. So now all 3 of our discoveries from October 2003 have names. Our final little tale is the first predicted impact by a near-Earth object. Again, this is in October 2008. The telescope out on Mount Lemmon in Arizona discovers a new object, which isn't unusual. They can find a dozen a night depending upon where they're scanning. But this one piqued their interest because it appeared that this asteroid was on a collision course with the Earth. Not only that, but it was going to happen within the next 24 hours. And it certainly did. About 19 hours later, it exploded over the northern Sudan. It was really a unique opportunity. Not only could we study this asteroid in space, the outside layers, the spectral characteristics, but 24 hours later, we were going to have the ability to look inside it. So it was a first for a number of reasons. Once Monty Robeson heard about this, he jumped on the opportunity to put the camera on the telescope and go after it. This was a real challenge. It was very bright because it was very close, but it was moving so quickly that we had to take very, very short exposures with the camera so that it didn't smear across multiple pixels. McCarthy Observatory submitted some of the last observations of this object before it went into the Earth's shadow and disappeared. About 20 minutes before it disappeared in the shadow was our last observation. Only 2 other observatories submitted valid observations after that point. And the impact or the detonation of the object occurred around 10:45 p.m. Eastern Daylight Time. It was actually observed by a crew of a KLM aircraft that was traveling from Johannesburg to the Netherlands that night. They had been forewarned that they might see something in the sky, and sure enough, they had the time, the direction, so they looked in that direction at that time, and they saw the flashes of light way off in the distance of the fragmentation of this meteoroid. So here's one of the images that was taken that night. You can see it's down more or less on the left side of your screen. Asteroid 2008 TC3. Initial expectations was that it was too small to drop meteorites, but there were some folks out there that decided they would take a look anyway. And they did an exhaustive search, walking the desert floor, and they recovered almost 600 pieces of meteoritic material. I have to say, when we have a sample of this in our collection, this is probably one of the more complex meteorites that I've come across, because it's not a single, easily classified piece of stone. It appears that the parent body may have been subject to 2 or 3 collisions by different types of other asteroids. And so you got this real mixture of material. It's classified as a ureolite, but only about 70% of the meteoric material recovered fell into that classification. The other 30% was from totally different types of meteorites. It has characteristics of coming from a very primitive world. It also has characteristics of coming from a very evolved world, where the world has differentiated into a crust and a core and a mantle. It's got nanodiamonds inside it, diamonds that may have formed in the early stages of the solar system, diamonds that could have formed inside a complex body, or diamonds that formed from the shock of collisions. So a lot of interesting characteristics, and you just can't put this in one category. It's a very complex history, some of the history shows some melting, some of it shows some very primitive pre-solar system material. So something that I think that a lot of additional research will be done over time, and I wouldn't be surprised if there are some additional discoveries made on this particular meteorite. So again, we do have a very tiny sample. You can actually see there's some crustal material on the edge of the stony meteorite. But each one of these meteorites, and we have over 200 at the observatory, to me, what's more interesting than the actual meteorite is their stories, because each story is so different. In some cases, very entertaining, especially ones that go back several hundred years before people really believed that stones fell out of the sky. But I encourage you to take advantage of our collection. And that wraps up my Halloween tales.
Well, before you end the show, there's a few questions queued up for you. The first one is from Don, who wants to know what the blackened area of the 4 asteroid image is. I think that's the discovery image.
This area here is just an artifact of the camera. It's, I mean, what we would do if we wanted a image that was more presentable is that we would go through a process of taking a flat field and other ways of removing those artifacts. But it's just an artifact of the camera and the telescope optical system.
Thanks, Bill. And Lauren asked, what is it that about October that yields all the asteroids and meteors?
Well, nothing special about October. The Earth is continually bombarded by space debris. It just happens to be, since this was October, I looked at some of the events that coincided with the observatory and picked these particular happenings. But no, you can go through our collection and you can see every month of the year there's some very interesting falls and finds of meteorites. It's a very dynamic area. I'd say back when we were first started out, there were very few observatories around the world that were looking for these objects. But in the past 10 years, there are some major telescopes that have come online, and all they do is scan the sky looking for new bodies that have some kind of potential of interacting with the Earth. It's become more of a priority. So I don't expect that we're probably going to find any new ones, being such a small facility and having all these big guns out there that are searching the sky. But it certainly was, the time was right back then for these discoveries.
And one more, Bill. Trinette's grandma would like to know if any meteors have unknown elements.
Well, that's a very good question. There are elements that in many cases we don't know exactly how they were formed. Are they unknown? Boy, that's a good question. I hate to say yes or no on that one, but there's a lot of material inside meteorites that we come across that suggest that these rocks in space went through some very evolved process, whether when they were first formed or sometime later in their history when it appears that they interacted with other asteroids. But I can't say there's. I'd have to look up that question to give you a proper answer. There's some very interesting material that we come across. Material that predates the solar system, or material that suggests, well, we're not sure. Maybe it was contamination from some other world that it was blasted off of. If you remember a few years back, there was a meteorite that came from Mars, and there was a lot of press about potentially finding fossils in that meteorite. I don't think that went anywhere because the fossils were too tiny to be what they felt were viable. But we're always finding something different in these meteorites, and I hesitate to say that we've found everything yet.
And finally, Bill, other than the Peekskill meteor, what is another cool sighting you had?
Well, that's the only one that I've ever seen that produced a meteorite. I've seen plenty of fireballs, and a fireball is just a very, very bright meteor, something that rivals, say, the brightness of Jupiter or Venus. So I've had the pleasure, if you spend enough time outdoors, you'll see some very bright ones. And that's why we have these cameras that we're building. We have one installed at the observatory so that we can monitor the sky so we don't have to stay up all night. We have it all downloaded to computers that will search through those files and find any bright ones. So if we ever get another Peekskill that passes nearby and drops meteorites, maybe we will have the ability to locate them.
Thank you, Bill. Anything else for Bill? Okay, well, that's the end of our program for this evening. We want to thank you all again for joining us and hope that you'll be able to join us virtually next month again, and sometime in person in the future.